Merhabalar. Öğleden sonraki ilk oturumumuza başlıyoruz. Hello everyone, we will start our first session in the afternoon. There are 5 presentations in this session. The first one is implementations of the Needleman-Wunsch algorithm for GPU architectures, which will be presented by Furkan Kurt from Istanbul Technical University. Furkan, are you ready?
Hi. Can you see my screen? I think.
We are hearing you.
Okay.
If you are ready, you can start.
Yes. Hello there. My name is Furkan Kurt. I'm a master student in Istanbul Technical University. Today, I'm going to present our implementation of Needleman-Wunsch algorithm for GPUs. The first problem is similarity search is a main topic in bioinformatics or microbiology. It's the key factor of genome research, protein or medicine. And there are two approaches for this similarity search. One is global alignment methods that focus on partial similarities between two sequences, and global alignment methods that focus on entire amino acid sequences. And Needleman-Wunsch is one of the well-known, mostly used dynamic programming algorithm for global alignments. It needs three predetermined coefficients for match, mismatch, and gap. And it stores alignments on two-dimensional matrix, and each cell of these matrix represents a pair of amino acids and their alignments. And how these alignments are calculated? First, the score of a cell is calculated with the help of its three neighbors. One from up, one from left, and one from left. The score of its neighbors are summed with predetermined coefficients. Horizontal and vertical references are summed with the gap coefficient, and the diagonal reference is summed with the match or mismatch coefficient, depends on the pairing of those two amino acids. And maximum of these summations are taken as the score of that cell, and the alignment is determined according to where that score is derived. If it's derived from the diagonal reference, that means it's a pair match or mismatch, or it's derived from up or left references. That means it's a gap. And the Needleman-Wunsch algorithm has a quadratic time and space complexity that makes it hard to use with longer sequences. So parallelization techniques applied to improve its performance. And due to the data dependency of the algorithm, each anti-diagonal vector of the alignment matrix can be calculated simultaneously. To calculate the vector, two previous vectors are needed as horizontal, vertical, and diagonal references. After the calculation of the current vector will become horizontal, vertical reference, and the horizontal, vertical references will become diagonal references for the next iteration. And the process continues at the end of the matrix, the very top right cell. And we choose GPUs for parallelization due to their massive parallel architecture, and we use CUDA as our tool. So in usual implementations with CUDA, first kernel alignments are done, then it's executed, and after the execution, data transferred from device to host. And we implemented 3 techniques to improve its performance. One is changing the memory representation to make it more suitable for the Needleman-Wunsch algorithm. And second, dividing traceback matrix to increasing data transfer throughput. And the last one is using relatively new mechanism, cooperative groups, to reducing kernel launch overheads. Our first technique is changing memory representation. We use anti-diagonal major ordering because the classical ordering methods not very suitable for anti-diagonal vector calculations because 2 consecutive elements of a vector are stored distant addresses on the main memory. That makes it hard to transfer the vector from device to host and can cause memory faults such as cache miss or even TLB. And we use anti-diagonal representation. In that representation, 2 consecutive elements of a vector are stored in consecutive locations in the main memory that allow us to transfer that calculated vector directly to the host. And the second technique is dividing the traceback matrix. That technique must be used in some cases due to finite memory of GPUs. For longer sequences, the GPU memory can be insufficient. And it's also beneficial for increasing data throughput because transferring each vector at the end of an iteration is it's not using the whole bandwidth. And the last technique is cooperative groups. In early versions of CUDA and NVIDIA GPUs, there's no such inter-block synchronization mechanism. It must be done explicitly by calling kernel iteratively. CUDA 9 introduced a new mechanism, cooperative groups, that allows synchronization across blocks. It requires Kepler or Neewer architecture for hardware side and CUDA 9, at least CUDA 9 for driver side. And here is our setup. We tested our implementation with 32 gigabytes of RAM and with NVIDIA GTX 1650, which is a Kepler, which is a Turing device. We used datasets that has length start from 10,000 to 100. And we noticed the iterative kernel launch with anti-diagonal representation increased the performance 5 times when it compared to the serial approach. And dividing submatrix and launching with standard methods gained significant performance up to 15 times, and using cooperative groups increased even more to up to 17 times. And we look deep down to the GPU characteristics with NVIDIA Profiler, and we noticed the dividing submatrix has reduced the data transfer time significantly, and using cooperative groups reduced the overheads. And in conclusion, iterative kernel launch methods allow us to use massive parallel architecture and boost the algorithm performance. Dividing the traceback matrix increases the data throughput and gains significant performance. And using cooperative groups can increase performance by reducing the kernel launch overhead. Actually, that's all my side. Thank you all for listening, and thank you for organizing this conference and gave us opportunity to present.
Thank you so much, Furkan. Is there any question? Okay.
No one. Can you hear me?
Hardly.
Oh. So these cooperative thread groups, they have number of thread block limitation or the number of threads limitation. Did it cause any limitations on your implementation? If you need to run larger domain sizes, etc.
The cooperative groups can be launched with the proportion. I guess it's proportional with SM counts, the multiprocessor counts, and each multiprocessor can be launched with 1024 threads. In our setup, we have 16 multiprocessor. That means approximately 16,000.
Yes, but if you have a domain larger than 16,000. So
yes, and we used block synchronization across the larger vectors. The first part of the vector calculated, then the second part of the vector can be calculated. And they are independent from each other. So one core can calculate a value, then it can calculate another value within that vector, because they are independent.
Okay.
From.
Okay. Thank you.
I have also a question. Another question from the audience. Okay. I have two questions. The first one is, what is the cost of data transfers between the CPU and GPU? Is your algorithm data intensive or memory intensive? So what's the cost of memory copy operations between CPU and GPU? Is it negligible or not?
For traceback metrics or kernel parameters?
Cost of data transfer between CPU and GPU in each iteration of your algorithm.
Well, for our iterative methods, data transfer dependent on the vector size, the anti-diagonal vector size, and for submatrix iteration, it depends on submatrix size, and it's constant. We determined it empirically. It's like 2 gigabytes of data for a submatrix.
Thank you. And the last question, it seems the size of your global memory is not very large. So will you consider to implement your algorithms on a multi-GPU environment?
Yes, it's our plan to make it discrete algorithm. The map reduced like approach can be applied to it, because in our case, 100,000 is the limit, because after that, we don't have enough main memory to store that matrix. That cause TLB misses, and that makes disk to main memory transfer the performance of the execution time of algorithm increases significantly. That serial or parallel approach doesn't matter in that case.
Thank you very much again for your presentation. Let's continue with the second presenter. The second presentation is performance evaluation of CUDA optimizations for convolution operations. And Burak Topçu will present this study. And okay, Burak, are you ready? Let me check again. Yes, Burak Topçu.
Can you see my screen now?
The study named Performance Evaluation of CUDA Optimizations for Convolution Operations.
Okay, I'm starting. Hello, everyone. Today, I will present you a paper that we named as Performance Evaluation of CUDA Optimizations for the Convolution Operations. Here, I shared a QR code that links you to our GitHub repository where we share.
Burak, I'm sorry, we cannot see your presentation. Your screen has not been shared yet. Can you turn off the screen sharing and start again?
Okay, let me.
If you want, we can move on to the next one of the topic. So let's go to, yeah, so let's go to homework.
Okay. There's a problem on the screen of Burak Topçu. Let's continue with the third presenter. Then when Burak is ready, he will also present his study. Okay. So the next presenter and presentation is about accelerating graph embedding on a single GPU using graph reordering. It will be presented by sorry, I cannot. Okay. Alapsi from Sabancı University. Okay. Thank you.
Thank you. Okay, sorry about the delay. So this paper, Accelerating Graph Embedding on Single GPU Using Graph Embedding, by myself, Amro Al-Absi Al-Jundi, and Dr. Kamal Kaya from Sabancı University. Okay. So first of all, the outline of the presentation. First, we're going to introduce the paper, what our contributions are going to be. Then we're going to introduce graph embedding and specifically parameter partitioning-based graph embedding. Then we're going to talk about how currently partitioning-based graph embedding has imperfect utilization of the GPU due to its nature of memory copies. Then we're going to talk about some graph reordering algorithms that we used, then showcase our evaluation and our results, and conclude the presentation. So graph embedding is a procedure that creates from graphs a d-dimensional representation of their entities, because graphs are highly unstructured and hard to work with. And this d-dimensional structure is good for machine learning. Accelerating graph embedding using GPUs is not anything new. It's been being done for the last 2-3 years.
However, it's very costly, both in terms of time and memory. One way to bypass this memory restriction of graph embedding is to use parameter partitioning based algorithms, where the parameter space is partitioned and handled in batches. Still, this process is heavy in communication, and it is not as good as it can be. So what we propose in this work is to use graph reordering as a pre-processing step, and we show that it can significantly speed up the process. Our contributions are as follows. We show the effect of 4 different reordering algorithms spanning different parts of graph theory, let's say. And we show that they actually can benefit GPU accelerated graph embedding. We show that reordering, the simple step of reordering, can improve the performance by up to 2 times given a good graph. And we show the results of graph embedding given reordering on the quality of the embedding, not just on the speed of the embedding. So first of all, what is graph embedding? Graphs are highly relational data structures, but the representation is usually very unstructured, right? And it's hard to take a graph and do some machine learning on it directly. So what we like to do is to take these graphs and transform them into a standard d-dimensional representation, like the one you see over here, where every vertex gets a vector of numbers. This vector, of course, we don't understand it, by looking at it, but it does encapsulate information about the vertex itself. We can use it for things like predicting link in a graph. We can use it for classification of nodes in the graph, and many other different tasks. There are many ways to do this thing. The most successful or the most common is sampling-based embedding, where you pick samples from the graph, vertex pairs, and you either make them closer in the embedding space or further apart in the embedding space, given some objective function that you're working with. Again, many GPU algorithms do accelerate graph embedding, but we were going to be working with the tool that we proposed in previous work called GOSH. So what is parameter-based graph embedding? Parameter partitioning. So the graph embedding matrix, the matrix containing all the vectors of embeddings, is a pretty big matrix. Given like a real world graph of 40 million, 50 million vertices, the embedding parameters can span up to 20, 30 gigabytes. And now there are GPUs that fit this amount of memory, but before that wasn't the case. And still bigger, larger graphs still exist. So we have to be able to work with graphs that do not fit inside the GPU memory. And that's where parameter partitioning comes in. The way it works is, given the embedding matrix that we see over here, M, we partition the embedding matrix into smaller parts. And each part here has the vectors of a set of vertices in the graph. We send these vertices, these vertex sets, their embeddings back and forth to the GPU. And we do the computation on the GPU, where it's much faster than it is on the CPU. And at the same time, usually how it's done is the CPU, the host, while the GPU is doing calculations, carries out the sampling process, picking out the vertex pairs that we're going to make either closer or further apart in the space. This process is fast, but as we're going to see now in the next slide, it has some issues, especially with utilization of the GPU. So now I'm going to explain the GOSH method of doing this parameter partitioning. And it's shown in the pseudo algorithm. First, we start by partitioning the graph itself into K parts. Here, we don't use any smart partitioning. It's simply ID based. So the first few, the first X, second X, blah, blah, blah. And then we send some parts to the GPU so that the GPU will have some embedding parts at the beginning of embedding. Then we generate an ordering of carrying out embedding. What do I mean by ordering? I mean, technically, we would like to be able to carry out updates on any vertex pair in the graph, any 2 vertices. So what that means is we need to have it such that in every training epoch, in every loop over the graph, every pair of vertex sets must exist on the GPU at the same time. Otherwise, there can be vertices or edges that cannot be updated at the same time. So this over here shows the order of carrying out the updates. So what this means is, the way we carry updates is we first move the first vertex set to the GPU, and we carry out updates where vertices exist in this vertex set. And the second update set will be with vertices where one end of the sample is in vertex set 1 and the other end is in vertex set 0. And then here it means carry out updates on vertex set 1 and 1, 4, 5, 6. So this ordering of carrying out the updates is not arbitrary. The literature suggests that this is the best in terms of quality of embedding, in terms of machine learning performance. This type of updates does the best because it basically allows updates to not to be carried out randomly, and it allows updates to not to happen on isolated parts of the graph too often. So now this is the essential part about the algorithm. The way it works is, this is a very high level view of it, is we would pick out these pairs, 0, 0, 1, 0, 1, 1, 2, 0, 2, 1. We pick them out from the graph or from the in-out ordering that we generate. And then for every part pair, ij, if that part of the graph, if the vertex set I and vertex at j have some edge inside them, in other words, can have potentially samples inside them, then we would send them to the GPU. We would send the samples to the GPU and carry out updates. If there are no samples, if there are no possible samples that we can get out of that particular part pair, then we do not bother doing the update. We don't even send the GPUs. Because for example, let's say that there are no samples possible to get from this part pair 5. So vertices in the part 2 and vertices in the part 1. It would be pointless to send the graph embeddings, which are big, by the way, to the GPU to do very few updates or no updates. So this is kind of the thing that we capitalize on with this algorithm. So now let's talk about the imperfect utilization of the algorithm as it is implemented right now. Because of the sparsity pattern of a graph, part pairs will not be used equally. So if you look at an adjacency matrix of a graph, you'll see that edges are not exactly split up in an even manner. You're going to find that some places in the graph have more edges inside them, more potential samples than others. So if you just send out your embedding parts to the GPU in an arbitrary order, then you're going to end up with something like this. This is the utilization. This is the NVIDIA Visual Profiler output of the graph. This is a Stockton-Weibull graph. Okay, smart, sorry. So this is the NVVP output of a certain graph. And here we can see the memory copies between the CPU and the GPU. And this is the computation. We see that there's a very significant amount of idleness happening on the GPU in terms of computation. And the reason is this. Let's say we send this embedding part to the GPU, but then the corresponding block in the adjacency matrix is empty, has very few samples. What that means is we just sent a huge chunk of data to the GPU, hundreds of megabytes, potentially gigabytes, for very few updates on the graph itself. So what we're suggesting with this paper is take this graph, reorder it in such a way that you change the sparsity pattern of the graph to allow for empty patches in the adjacency matrix. These X's here represent empty patches, meaning no edges exist at all, no samples. And then while you're carrying out the embedding updates, what you're going to end up with is very few copies, or at least less copies than you'd have here, because when there's an empty patch, you don't even need to send the embedding part to the GPU, and you won't have to do any kind of unnecessary updates. So what we're going to do now is we're going to use 4 different reordering algorithms and see how they affect the graph embedding performance. So first, we're going to introduce 2 fill reducing algorithms. Simply, fill reduction is an objective where you take a graph and reorder it to help if the graph was an AX equal to B linear system. Fill reduction is an objective that allows this linear system to be solved faster. And it turns out that it's very helpful for graph algorithms as well. So 2 objectives that we're going to optimize here are bandwidth minimization and minimum degree. Bandwidth minimization is when you take a matrix and reduce or minimize its bandwidth. The bandwidth is basically the distance between the diagonal and the furthest non-zero from the diagonal. Minimum degree means reorder the graph very simply in terms of the minimum degree of the vertices. So starting from the smallest degree all the way up to the biggest degree. We also use graph partitioning and clustering algorithms. These are algorithms that take the graph and split the vertices of the graph to optimize some objective. And these algorithms are usually smarter. They don't just want to reduce bandwidth or to go by degree. They actually try to. So for example, here we have 2 algorithms: Grappolo clustering and partitioning with Metis. With Grappolo, you try to partition the vertices in such a way that you maximize the number of edges within a partition, within a cluster. And with Metis, you try to split the graph into 2 parts to minimize the graph edge cut, which means the number of edges between the 2 parts. So these are more sophisticated algorithms, let's say. So with these reorderings in mind, now we're going to show the results of how they actually help embedding. So we have 6 graphs that we're going to be working with. Hyperlink is a web graph, so websites connecting to each other. Twitter, Sinaweibo, and Friendster are social networks. Road USA and Europe OSM are road networks. So they represent roads on the street. We're going to use 2 architectures. One we're going to use for embedding, because remember, the graph embedding is a GPU-based algorithm, and this server has a GPU, a Titan X GPU. And the other architecture does not have a GPU, but it has a bigger memory. And the reason we do this is because for Metis and Grappolo, the more sophisticated algorithms, this server is not able to reorder all the graphs. So we had to, use a different server for this particular task. So let's talk about the reordering results first of all. First, if we look at Grappolo, remember this is the clustering based, this is the partitioning based. We see that they do what you think they do. So they move more edges to the diagonal of the graph than the original. So this is the no reordering. This is the original graph. This is what the adjacency matrix looks like after you reorder the graph. So Grappolo and Metis, they kind of behave the way you expect them to. They put things in the diagonal. However, you'll notice that both Grappolo and Metis don't lead to any empty patches in the graph, meaning that yes, the adjacency pattern, the sparsity pattern is different, but it does not give us the objective that we're looking for, which is give us empty patches in the graph so that we don't have to move data to the GPU at all. However, the simpler algorithms, RCM and AMD, perform very well in terms of this specific objective. So AMD performs incredibly well, and depending on the graph, obviously, but we can see that for all the graphs, it leads to some empty patches in some areas. And RCM behaves almost similar, not as good as AMD, except for this, the road network, but it still behaves well. It actually does lead to empty patches. And also in terms of speed, the more sophisticated algorithms are much, much slower than the simple algorithms, as you'd expect. So RCM is 28 times faster than Grappolo, 14 times faster than Metis. And it's more realistic, as we're going to see now, to use it with embedding. And we also find that it's actually faster than ASM. By the way, all implementations here are serial. There's no parallelization for fairness, because not all algorithms are parallelized. So these are the important results here. So in this graph, we show for every graph how this particular reordering helped the embedding. So this is the improvement in runtime of the embedding because of this reordering. This is the reduction in the number of memory copies because of the reordering. This is the reduction in the number of kernels executed because of the reordering. Keep in mind, all reorderings lead to the same number of updates. It's just a matter of how many kernels we run, how many dispatches to the GPU happen. So like the last figure shows or tells us, Grappolo and Metis don't really lead to any reduction in kernel execution or copies. We still have to do all the memory copies, all the kernels execution. And we see that their effect on runtime is not exactly significant or unpredictable, to say the least. So generally, there's almost no difference when you add Grappolo or Metis, except for the one particular graph, Sinaweibo, but we were not able to exactly give a reason for how Sinaweibo was behaving with any of them. But the consistent result is that RCM and AMD significantly help the embedding time. So we see here that both RCM and AMD can go to up to 50% improvement in embedding time. So basically 2 times speed up, thanks to reordering, just because we lead to these empty patches in the embedding. And they reduce the number of copies, and they reduce the number of kernels dispatched. Of course, these results are cool, but is reordering justified? Because it's an additional overhead cost, right? So looking at this graph, we see, given a reordering, how long the embedding takes without reordering, how long reordering takes, and then the total time with reordering, given like embedding and reordering, and finally the improvement. So the improvement meaning, how much have we improved from going from only embedding to reordering plus embedding? Grappolo never improves. Sometimes the reordering actually takes longer than the actual embedding needed. Metis, also no improvement at all. Again, the reordering is very expensive, is not justifiable for this particular use case, but RCM and AMD still 50% and up to 50%, 50%. Their average is around 30%. So again, results show that using reordering, simple reordering that leads to this very specific objective of emptying out the adjacency matrix is very helpful. Finally, this is the last slide of the results. We have the link prediction accuracy. So link prediction here is a machine learning task that we use graph embedding for. We find that So what we first expected was that the link prediction results don't get affected. We're not really doing anything that has to do with the algorithm itself. We're just changing the order of things. But surprisingly, we find that reordering does change the accuracy. In our case, we find that reordering always improves the accuracy, but we're not really exactly, we can't like give that as a final judgment because we can't explain why a certain reordering gives us better embedding. But what we find is consistently different results. What I mean is that the order, the significance of, or not, let's say the order of behavior is the same. What I mean is, as the number of training epochs increases, the relative order of reorderings stays the same. So for example, here, as you increase the number of epochs, RCM reordering always gives us the best accuracy. As you increase the number of epochs, what's it called? Metis reordering always gives us the best accuracy. Here, as you increase the number of epochs, also Metis reordering gives us the best accuracy. So what we can take from this is that reordering does, let's say, change the quality of embedding, not just the performance of the embedding. And we want to do further research and understand these effects more. Okay, finally, so graph embedding on GPUs often suffers due to memory limitations. And parameter partitioning is not something we came up with. It happens and it helps this process significantly. But we show that graph reordering does improve the performance. If you do it well, if you have a specific objective fast, you can get considerable speedups. But you need to have a reordering that's fast. And you need to have the sparsity pattern that you get to needs to have a lot of zeros. These are the objectives that we have so far. In the future, we want to examine reordering on embedding quality. So understand why the embedding quality changes. And we want to change the scheduling of the kernels in such a way that not only does it exploit empty patches, but it also exploits low density patches as well. And that is all. Thank you so much for listening.
Thank you so much, Emrah. Do you have any questions?
So can you do better than RCM or AMD? Like, is there,
well, honestly, right now, what we're thinking of is improving AMD itself. So we're trying to have an approximate degree algorithm that makes AMD faster because we found that AMD is already pretty good. Yeah? So, but we don't have any other reorderings in mind.
But is the objective of AMD the same as your objective? Or is it?
No. So, like we don't have any ordering that is what's it called optimizing for our specific objectives. We are right now just going through the orderings in the future and seeing how they give us the like what we want. But it can be a good direction to actually try to optimize for that specific objective of the character.
Okay, another question. Any question from the chat panel? Okay, thank you so much for the presentation. Okay. Okay, Burak, are you ready?
Yes, I am. Sorry for the before disruption. I cannot connect. I cannot share my screen, so I need to restart Zoom application. Can you see my screen now?
Yes, now it's okay.
Does my voice is clear too?
Yes.
Okay.
And you can start your presentation. Thank you.
Okay, thank you too. Hello everyone, I am Burak Topçu. I am an MS student in Izmir Institute of Technology. Today I will present you a paper that we named as Performance Evaluation of CUDA Optimizations for the Convolution Operations. Here I've shared a QR code that links to our GitHub repository where we shared our experimental results and experimental configurations. Here is my outline. First of all, I will make a general overview about the convolution operations. I will explain some problems. Then I will share our motivations and evaluations. Then I will describe the CUDA optimizations for the convolution operations, such as constant memory usage for the to hold masking arrays, shared memory usage in order to prevent from repeated global memory access, and usage of CUDA streams to prevent
memory copy operations. Actually, the latencies arise from the memory copy operations between CPU and GPU. Then I will share our evaluations with mentioning our experimental setup and experimental results. Finally, I will conclude my presentation. As you're familiar with the convolution operation, there is a visualization for the convolution operation. In the convolution operation that we try to optimize is taken from the Polybench benchmark. In this convolution operation, they used 9 masking elements. By shifting this masking array on the all input element, they calculate the convolution result. The algorithm 1 shows the pseudocode for the convolution algorithm. As you can see, the C11, C12, and the other C elements are the masking elements. A is the input and B is the output arrays. This is a profiling results obtained from Insight Compute tool. As you can see, compute units or streaming multiprocessor utilization and memory utilization is lower than 50%. And this is a problem. This problem caused by the repeated global memory access between global memory and DRAM of the GPU and streaming multiprocessors. We have also another problem, as you can see from the figure 3. Figure 3 represents the Insight system profiling, overall execution performance of the 2D convolution algorithm. As you can see from the green bar and pink bar, memory copy operation between host and device consumes most of the elapsed time. Lastly, there may be another problem because of the usage of masking array. They implemented algorithm such that masking arrays are held in the local register resource of streaming multiprocessor. It can decrease the active thread amount at runtime. Our main motivation is solve the aforementioned problems by avoiding bringing the same input element from the global memory to the streaming multiprocessor by benefiting from the tiling approach. We also try to reduce elapsed time shown in the before figure for the memory copy operations between host and device. And we also try to increase the number of active threads by moving masking elements into the constant memory. Our contribution is that we optimized 2D and 3D convolution algorithms given in Polybench benchmark with some CUDA optimizations and present the optimization results in a systematic way and verified our results by Insight Compute and Insight Systems profiling tools. For the evaluations, we achieved 1.6 and 1.33 and 1.58 and 1.27 faster overall GPU kernel and GPU kernel execution performances for 2D and 3D convolution algorithms respectively. In the baseline version of the 2D convolution algorithm, they implement the masking arrays as kernel as variables in the kernel. These variables are held in the local register of each thread. This can reduce to active threads at runtime. In order to increase active thread amount at the runtime, we move these masking elements into the constant memory as shown in figure 5, sorry, to prevent, there can be several results for the masking, for moving masking array into the constant memory, such as it can degrade the performance because accessing registers can take less time compared to the constant memory. Also, it can increase the GPU kernel performance because we can enable more active threads at runtime. We should note that constant memory accesses for 2D convolution operation will occur very close to each other because all threads will follow a similar execution path because there is no branch divergence or there is no data dependency. This will increase the utilization of constant memory. Secondly, they did not benefit from the shared memory for the baseline version, and it degrades the performance. As you can see from the figure 6, accessing shared memory from an SM is a off-chip memory access, and it takes lots of memory cycles. However, if we try to access on-chip memory access, such as accessing shared memory from a thread 00 or thread 10, takes less cycles compared to access global memory. For the baseline version, accessing global memory degrades the performance because of the access latencies. Also, it can cause high traffic on global memory bandwidth, because in order to calculate convolution operations, there occurs lots of repeated memory access for the same elements. In order to save from these performance degrading factors, we benefit from tiling approach by using shared memory. For a scenario where thread block size is 32 by 32, whose tile size is 34 by 34 in order to include surrounding elements, in order to read all elements required for this thread block, by the way, this thread block is 00. In order to read all elements required for this thread block from the global memory, we moved the required elements to the shared memory at initial step. Then we are accessing shared memory repeatedly instead of accessing global memory. We expect that this will increase the utilization of overall GPU kernel execution. In this way, we expect to decrease traffic on global memory channels, and we hope that we save from the global memory access latencies, because shared memory access latency is comparably small compared to the global memory accesses. The last optimization approach for the convolution algorithms is to benefit from CUDA streams. As you can see from the figure 8, as I mentioned before also, most of the overall execution time is consumed during the memory copy operations between host and device. In order to save from this performance degrading factor, we implement CUDA streams. We benefit from the CUDA streams. As you can see from the figure 9, we overlap the memory copy operations between host and device. In this way, we increase the performance of the overall execution of convolution operations. Here, our first experimental setup. Our first experimental setup is GTX 1650 GPU. This GPU is built upon Turing architecture. This GPU has 14 streaming multiprocessors, where each SM have 64 cores. Also, this GPU has 64 kilobyte L1 cache per SM. We have used CUDA toolkit version of 11.4. For the second experimental GPU, we have used Tesla K80 GPU supplied by Google Colab. This GPU is built upon Kepler 3.0 architecture. In this GPU, we have 13 streaming multiprocessors, where each streaming multiprocessor have 192 cores. Also, this GPU has 16 kilobyte L1 cache per streaming multiprocessor. However, developers can increase this L1 cache size up to 48 kilobytes. Also, we have used CUDA toolkit version of 9.1 in this experiments. We create different scenarios for the experiment configurations. The first three are the our main optimization techniques, and we try to combine those optimization techniques to each other to increase to get better performance results, such as using constant memory and shared memory together, constant memory and CUDA streams together. Also, we have used a final configuration which includes CUDA streams, shared memory, and constant memory usage together. For the experiments, we have used 3 different data sites for both 2D convolution and 3D convolution algorithms. In these algorithms, input data is generated randomly. Masking elements are constant as in Polybench benchmark. All of the elements, including input data and masking array and output data, are all 32-bit float variables. Thread block size for 2D convolution algorithms is 32 by 32, and thread block size is 16 by 16 for 3D convolution algorithms. We have used 8 CUDA streams for the CUDA stream implemented version for both 2D and 3D convolution algorithms. Here you can see baseline and shared memory included profiling results for the 2D convolution algorithms. Figure 10 shows the baseline profiling results. As you can see, all of the memory operation between kernel and all of the memory operation carries out on the channel between global memory and kernel. However, when we include shared memory, the load on the global memory channel is reduced, and the channel between kernel and shared memory is activated. For example, the request between kernel and global memory is decreased, and the request between shared memory and kernel is increased. As a result of this, the throughput value for the shared memory implemented version is increased, as you can see from the figure 11. The compute unit utilization, for example, is above 60%. Similar case is valid for the memory utilization. Those are the experimental results. Table 1 shows the experimental result for this. For the experiments tried on Tesla K80 GPU, we observe performance enhancements for GPU kernel execution times. For example, by the way, first row shows the GPU kernel execution times, and second row shows the overall execution times, including memory copy operations between host and device. As you can see, GPU kernel execution time for the experiments tried on Tesla K80 GPU, we achieved performance enhancement by using shared memory compared to the baseline version. However, we cannot observe similar results for the GeForce GTX 650 GPU because Turing architecture determines L1 cache usage at runtime at most optimized way. When we include shared memory usage for the GTX GPU, it degrades the usage of L1, so performance gets degrading. However, Tesla K80s holds separate shared memory space at runtime. So if we activate shared memory for the Tesla K80, we can increase the performance. Those are the constant memory usage results. Table 2 shows the experimental results for 3D convolution algorithm, while table 3 shows the experimental results for 2D convolution algorithm results. Since 3D convolution algorithm has 6 more constant memory elements, when we include constant memory usage for the 3D convolution algorithm, it affects performance a bit negatively compared to the 2D convolution because 3D convolution threads needs to bring more data from constant memory, which degrades performance a bit. However, when similar to this, when problem size gets bigger, as in the last experiment of 3D convolution, using constant memory degrades GPU kernel execution performance more. Holding masking elements into constant memory is a trade-off depending on the register resource amount, performance, and the number of elements in the masking array. The last results represents the usage the last results for the usage of CUDA streams. When we use CUDA streams with the number of 8 CUDA streams, we obtain better results for both GPUs for the overall execution time, as you can see second row of the experiments. If we increase the number of CUDA streams, it degrades the GPU kernel execution time because we are adding kernel launch overheads by increasing the number of kernel launch. However, since memory copy operations takes comparably large time compared to the kernel execution, the overall execution time decreases when we increase the CUDA stream amount. For the results, including...
Sorry, can you present faster? You have reached your time limitation.
Okay.
Can you present faster?
Okay. To conclude, including shared memory into the and 3D convolution algorithm results in performance improvement for the Tesla K80 GPU, but does not change performance too much for the GTX GPU because current GPU architectures such as Turing use L1 cache in a fully optimized way by determining the usage of L1 cache at runtime. Constant memory usage can eliminate unnecessary register usage for the masking elements, even if it does not significantly affect the performance for the baseline versions. However, if the convolution operations works with more masking elements, such as a 7x7 or bigger size, holding masking elements into constant memory will likely increase the GPU kernel performance because it prevents stalling active threads when a thread block is issued. Also, adding CUDA streams to the baseline version of the convolution algorithms increases the performance by hiding the elapsed time for the memory copy operations. That's all on my side. Thank you for your kind listening. If you have any question, I will glad to answer them.
Thank you so much, Burak, for your presentation. Do you have any question?
I do have, but I don't want to take time, so that's fine. So, Burak, have you tried comparing Kutlas convolution implementation?
No, I did not compare.
Templated convolution library. I suggest you compare layers.
Okay, thank you. I did not compare it, by the way.
So take a look at Kutlas.
Okay.
It's like Atlas, but Kutlas. Okay.
Okay, thank you.
Okay, another question? Any question from chat? No. Okay, thank you again, Burak, for your presentation.
Thank you.
Okay, continue with the next presentation. The name of the presentation is GPU Accelerated Floating Random Walk-Based Transient Heat Conduction Solver. Will be presented by Ersin Yıldız from Özyeğin University. Okay, Ersin, are you ready?
Yes, can you hear me?
Yes, we can hear you.
Okay, hello everyone. My name is Ersin Yıldız. I am a PhD candidate in Özyeğin University in Mechanical Engineering Department. My presentation is on GPU accelerated floating random walk-based transient heat conduction solver. In this presentation, I'll start with a brief introduction. I'll explain the floating random walk methods. Then I'll show the verification cases and the results, and I'll draw a conclusion. Under the continuum assumption, most of the heat transfer processes are governed by differential equations. There are diffusion terms for conduction and advection terms for the transport of a substance. And sometimes we encounter integral differential terms for example, in radiative heat transfer. Numerical methods to solve heat transfer problems can be classified into two categories. Deterministic methods such as finite difference and finite volume discretization based methods, and probabilistic or statistical methods in which the population means are calculated by means of a large number of samples. As probabilistic methods, Monte Carlo and random walk methods are frequently used in heat transfer and solutions. In this study, we focus on the solution of conduction heat transfer problems using floating walk methods. The objective of this study to implement floating walk method on graphical processors and to evaluate its feasibility for conduction heat transfer problems from accuracy and computational cost point of views. Before floating walk method, it is helpful to understand the general idea of the other walks and applied to heat conduction problems. We consider transient. We consider the transient heat conduction with constant material properties and prescribed temperatures at boundary. We aim to calculate the temperature at this point at time t0. After manipulating the differential equations with finite difference schemes, we obtain the following equation. It means the temperature at time n+1 is a function of the temperatures of the neighbors at time n. We release a particle from the point and perform consecutive steps in each direction is determined by drawing numbers. Here, the probabilities of directions are the same and equal to 1/4. Using this procedure, a large number of particles are traced until they are absorbed by a boundary. Now let's look at floating random walk methods. We again consider the transient heat conduction problem with constant material properties and Dirichlet boundary condition and uniform initial conditions. After applying Duhamel's theorem, the governing equations we obtain this integral relation in spherical coordinates for the temperature at a center point of a sphere. In this relation, R is radius of the sphere, omega is azimuthal angle, phi is unit angle, and tau is time decrement. And the functions f, g, and h are probability distribution functions, in short PDFs, that's formulated as shown. F and g are for space quantities, namely omega and phi, and h is for time quantity tau. What this relation tells us is that the temperature at the center point is a combination or integral of the temperatures at the surface points on sphere at some time t0 minus tau. Now, we first focus on the calculations of the temperature at the center point of a sphere at time t0 by a floating walk. In the first step, we initialize a particle at the center at time t0. Then we draw random numbers, and we sample omega, phi, and tau for this particle. Sampling of omega and phi is simple. The formulas are shown. Tau can be sampled from pre-calculated and tabulated values. By doing this, in fact, we calculate a direction and time decrement for the particle step, a step from the center to the surface of the sphere. After that, we can easily calculate the particle occasion and the time that the particle arrives to sphere surface. Then the particle records the temperature of the point where it arrived, and the particle is terminated there. Finally, we do this procedure for a large number of particles, and means of the recorded temperatures of the large number of particles gives the temperature at the center point at time t0. Now for a general domain, this procedure is very similar. In this case, the particle performs consecutive steps until they are absorbed at a boundary. There is a boundary strip thickness denoted as R-min, which represents a threshold for a particle being considered at the boundary or not. This time, the radius of the intermediate spheres in the integral equation is Ri, which is the shortest distance to boundary from the current point. The rest is nearly the same. The computational algorithm is as follows. For each particle P, we initialize the particle as before. We calculate the shortest distance to boundary, Ri. By doing this, we draw a largest imaginary sphere inside the domain centered at the current position, whatever the position is. Then we compare Ri and R-min. If Ri is smaller than R-min, it means that the particle is very close to boundary. Therefore, the particle is terminated there because it is absorbed at that boundary. And the temperature is recorded. If not, we sample from the PDFs just as before, and we take a step. In other words, we update the position and the time of the particle. Then the particle needs to go to step 2 to perform its travel until it is terminated. After all the particles are terminated, the temperature is calculated by averaging recorded temperatures. It should be noted that in the computational algorithm that we implemented for GPU is very similar to the algorithm explained here. We simply launch a maximum number of threads that the used GPU can execute simultaneously, and each thread gets a particle from the particle pool and do the calculations. Once the particle is terminated, the thread gets another particle and do the calculations for that until all the particles are terminated. In floating random walk method, all the 3 types of boundary conditions can be implemented. All the changing part is the behavior of the particle when it arrives to boundary. During particle's travel, the particle is terminated only if the particle arrives an absorbing boundary or the total elapsed time for the particle exceeds the time domain. Now, we have solved 3 test problems in the paper, but here I'll skip the second one due to time consideration. The first problem is steady state heat transfer in 3-dimensional semi-infinite domain. The lengths in x and y dimensions are 1 meter. The boundary conditions are as shown. Specified temperature as 0 Kelvin at the most boundaries, except that the boundary y equals 0 is insulated and the temperature is 100 Kelvin at z equals 0. The analytical solution is available in the given reference. There are 4 sensors where the temperature is to be found within the domain. The parameters of floating bulk are as shown here. In the first table, the analytical solution and the floating bulk solution are compared. As can be seen, the results are very similar. In the figure right side, the standard deviation is demonstrated by different number of particles. When the number of particles increases, standard deviation decreases as expected. In the second table, the single thread CPU code is compared with GPU code with regards to computational time cost. For large number of particles, there are big speedups in GPU computing. The last problem is transit heat transfer in three-dimensional cube. The cube centered at origin has 0.01 meter edge length. The maximum time is 10 seconds. The material is considered as copper. The boundary conditions are as shown. There is a specified temperature as 300 Kelvin. There is an insulated boundary, and the rest boundaries are specified heat fluxes. The initial condition is 300 Kelvin. There are three sensors where the temperature is to be found. And comparison between floating wall solution and OpenFOAM, which is a open source CFD finite volume based solver. The comparison has been made. In the OpenFOAM simulation, the finite volume mesh has 87 cells in each dimensions, and the time step is 0.1 second. The temperature history at the sensors are plotted in the figures. The OpenFOAM solutions and the floating bulk solution are very similar. The difference between the solutions is below 0.1 Kelvin. And the time cost of the floating bulk solution on GPU for three sensors is lesser than OpenFOAM solution on CPU, but this is a single thread computation. Now, in conclusion, floating random walk-based transient heat conduction solver has been developed. The developed solver has been verified by 3 test cases. Floating walk has following advantages. Its code development is relatively easy, but not for the best efficient code. No volume mesh is required, so no discretization errors inside the domain. Temperature can be calculated only at desired locations. It has a potential use in inverse heat transfer solutions, and it is suitable for parallel computing. It has some disadvantages as well. The algorithm requires an efficient shortest distance to boundary routine for complex shaped geometries. It has some difficulties with radiative boundary conditions due to non-linearity, but some approaches exist, such as linearization with heat transfer coefficients. And lastly, it is not the best choice when solving for the whole domain or for a large number of sensors. This study is supported by Center for Energy, Environment and Economy at Özyeğin University. Thank you for listening to me.
Thank you so much, Ersin, for your presentation. Okay, do you have any questions? Any question from chat panel? Okay, I have one question. Can you navigate your presentation to page 6? Sorry, page, okay, this one, okay. So which of these steps are implemented on the GPU?
All of them, the time.
So do they run in a single kernel or multiple kernels? Or in other words, is there any dependency between the steps?
They run in a single kernel, so they are sequential from top to bottom.
So, for example, in the third stage, or I mean, is there any dependency between these operations, or all of the threads can execute them in fully parallel? Or Dependency.
All particles are independent to each other. So that's why the particles are independent and can run simultaneously.
Okay, okay. Thank you very much.
You're welcome.
Okay. Thank you again for your presentation.
Okay. Thank you, you too.
Okay, let's continue with the next and the last presentation of this session. Sorry. Okay. The name of study is Feasibility Study of Adding GPU Support on SU2 with ILU0 Preconditioner. Will be presented by Didem Onat from Koç University.
Tamam, şurada dursun. Buradan açmama gerek yok sesini. Okay. Okay. So this work mostly done by my PhD student. He graduated, so I'm presenting on behalf of Najib. And it's a collaboration with Roketsan and Koç University. If you attended Mateus' talk in the morning, he mentioned two types of research. One is relevant, one is excellent. So this is more like relevant. So we did a feasibility study porting an ILU preconditioner to GPUs and whether it's possible to integrate this in SU2 CFD library. And tomorrow you can listen my student Aditya's talk for excellent. So he'll do a better job than me. Okay, so in terms of background, SU2 is an open source CFD computational or dynamics code. It is written in C++ and uses MPI, OpenMP very nicely for multi-core parallelization. And you can think maybe it's not an exact alternative for OpenFOAM, but it's very modular, nicely implemented huge library. And it includes multiple linear solvers like GMRes, BiCGStep, CG, etc. If you are coming from CFD world or mechanical engineering background or petroleum engineering or aerospace engineering, you're probably familiar with these solvers. And they support a number of preconditioners, including ILU. And our motto was here, can we assess the suitability of SU2 for GPU acceleration, because it doesn't have GPU support at the beginning. And we wanted to do this study and introduce GPU-based ILU preconditioner in SU2, whether it's possible or not. So GPU-based ILU preconditioners, you can write your own preconditioner, of course. There are actually a lot of ILU alternatives besides NVIDIA's cuSparse implementation, like ELMC and sync-free implementation of ILU. Actually, Najib's thesis was focusing on the sync-free implementations of ILU. But in this project, and one requirement from Roketsan, that they are interested in blocked ILU preconditioner because they were solving a number of unknowns per data point. So we needed a block ILU, and these sync-free and LMC algorithms, they don't support block form. They only work scalar. And cuSparse, it has blocked ILU preconditioning. And so we decided to use cuSparse for the purpose of this project. And ILU preconditioners, they have these two phases. The first phase is the analysis phase or / build phase. They analyze the metrics pattern and then discover the parallelism, build the data structures, etc. So this is kind of the preparation phase. And then there's a solve phase where they solve the triangular system. And cuSparse provides the functions for those analysis, factorization, and solve. So in order to integrate this ILU precondition and SU2, we have to do a number of things, understand how the SU2 linear systems work, understand their data structures, what kind of code modifications needed or additions, or which classes needs to be updated, or which attributes or variables needed to be added, and then change the build system so that it can compile nicely with CUDA programs and libraries and verify the code correctness, because we are solving a linear system, so we need to make sure that it still solves the same linear system, and then test its performance, of course. So I'll be quick explaining the changes that we made in the SU2, because I don't know if anyone uses SU2 here. Here it is. Okay, nice. At least there's one person. Okay, so there are some wrappers we added so that instead of calling the SU2 versions of linear system, it is we'll call the GPU's cuSparse system. And in SU2 there is system metrics class, which represents these matrices, and we had to introduce a number of variables and then functions to handle the GPU data structures and required for the GPU execution, and of course data transfer. So so what we did is in this wrapper, this function copies the input arrays to GPU, performs the solve, performs backward solve, forward solve, and then copies back to the CPU. And if you know GMRes, the preconditioner is done, and then you continue with other operations like you do sparse matrix vector multiplication, etc. And then so you have other operations in the solver. So ILU is one part of it. That's why we need to transfer the data back so that we can handle the rest of the solver on the CPU. So in terms of evaluation, we looked at state-of-the-art multi-core as a to make a fair comparison. So we use AMD EPYC, which contains 24 cores, and then Cascade Lake, which are one of the latest Intel architectures containing 28 cores. And we are using Tesla V100 as a comparison. So I consider these as, fair comparison. One architecture is not very old, or the other one is not very new, etc. So these are the simulation inputs. To me, they don't mean much, but for mechanical engineers or computational scientists, they mean a lot. So Rocketsun provided these kind of information for us. And correctness verification. So CPU and GPU results match, which is good. So we are not doing something wrong. And we did this for different mesh sizes. In terms of performance, we tested 8 million, 13 million, 20 million meshes, and 20 million was the largest that we were able to run on the GPU without exceeding the memory capacity. And we have 32 gigabytes of memory on the GPU. So here are the results. So on AMD, compared to AMD, so these are speed up of V100 over AMD. And on AMD, we are using all the 24 cores. We are not, not using one core. We are using all the cores and doing MPI parallelization, not OpenMP. MPI will be better, more suitable for this. So here we are seeing 20 to 30% improvement. But when you compare with Intel, we are actually slowing down. So Intel is performing much better here. So V100 doesn't have any performance advantage over Intel Cascade Lake. So if we kind of deep look inside what's going on, so the solver actually has these parts, Navier-Stokes solver, SA solver. And each solver has a, remember at the beginning I said there's an analysis phase and then the solve phase. The analysis phase is where you build the metrics and do the factorization. So the build stands for those, the analysis phase and then the compute phase. In fact, GPU is much faster in the compute phase most of the time, at least for the Navier-Stokes. But in the build phase, it kind of ruins the performance. So all the preparation or the analysis and the factorization is much slower on the GPU. So overall performance is, at least against Intel, is not very good. So then we break down the build phase versus compute phase of the overall execution time. As you see on the CPU architecture, build phase is 35% over 65%. So build phase takes 35%, but the rest is on the 65% is on compute. And in the Intel, it's 35 to 64. It's roughly similar, but on the GPU is the opposite. 77% is spent on the build phase. When we increase input size, it drops a little bit, but still over 70% is spent in the build phase, which I'm not showing here in the compute phase. Actually, GPU is very fast. Half of this time is spent on the data transfer. So 23%, in fact, actually 12% is the compute, and then the rest is the data transfer time. Okay. So in summary, in conclusion, what did we learn from this? Yes, it's feasible. We can call GPU functions or libraries inside SU2. But the question is whether it's worth it. Do you get any performance benefit? With this study, it's unpredictable, at least. Like if you have a, for Intel, we didn't gain any performance. For AMD, we gained performance. So you may get very little performance benefits at the end of this, study. But there are other things we should talk about. Like, did we use the best implementation of ILU solver on the GPU? We use cuSparse, which is ready to use, nice. There are faster implementations, like ELMC is sync-free, but considering they're faster, but they are not 50 times faster. They are not 2 times faster. They are 30% faster, 20% faster. But also they don't have the blocked version. They use the scalar version ILU implementation. So still, let's say you use a better ILU solver, maybe you will have 2x improvement on the GPU. And then you may say, why don't you do the build phase on the CPU? Because it's faster to do the build phase. And compute on the GPU. Yes, you can do that as well. The thing is, cuSparse requires you do the build phase on the GPU because it needs its own data structures. So on the CPU, you can write your own build phase. That means you need to write your own ILU solver on the GPU as well. That's the downside of using a closed source library, because we don't have any control over the build phase. If you can do the build phase very fast on the CPU and then have a blocked version of ILU written by us on the GPU, maybe overall performance will be much better. And we have plans for blocked ILU, but we haven't had a chance to implement it. Anything else that I want to mention here? Certainly, this is not an easy task. It required a lot of time to understand SU2 and how you need to integrate the GPU. But there's another issue that I should mention. on the CPU, you can use multiple, MPI processes, and you can actually go beyond multiple nodes, right, with MPI. But when you use GPUs, it's not very easy to do multi-GPU or ILU because load balancing communication between GPUs is very difficult. So unlike prior talks that we get, speed up performance benefits using GPUs, we cannot draw the same picture here for ILU because ILU is really hard to, very irregular, very data-dependent computation to execute on the GPU. Okay, that's all. One last advertising slide. If you are interested in doing master's, PhD, postdoc in our group, we can visit Parkour Lab. I have two projects, ERC project and Sparsity EuroHPC. This one, Kameroja is involved. We are together. And there's also a real ERC project. If you want to know more about them, you can email me or talk to me in a couple of days. That's all. Thank you. If you have any questions, I can.
So much for the presentation. Okay, do you have a question?
Yes.
Making up the question, some comments, and your response to your interest. B100 has mixed precision support. Really does shine in computations where there is some sort of different floating point, 16, 32, whatever, whenever they flow together. And this happens in machine learning when you have model quantization,
yes,
like that. And beats the heck out of CPU in summary. And would there be a case in here potentially?
I don't know, because when you play with precisions in a GMRS solver, etc. So I'm a little, so whether it will converge or not, I don't know. There are some studies with CG I encountered. We did some studies for SPMV, for example. The performance gain was small, 6%.
So those execution build and all those stages, if there's
yeah, there, but we didn't study in the overall solver. Maybe there might be opportunities for mixed precision here as well.
Not really.
But to be fair, you need to do mixed precision on the CPU as well, right? So because CPU supports 32 bits,
right?
Arithmetic is fine. Yeah. So I will consider that as an orthogonal optimization.
Yes. Just because you said B100.
Yes, yes.
Yeah.
So I should add, maybe if we ported the entire GMRes to GPU, we will get better performance. But I did a literature search on this, and there's not really a fair study doing a comparison with GPU versus CPU on like GMRes or very complicated these solvers. They compare with a single core, they compare with a very old multi-core, which is not fair. So even you fully port to GPUs, I think you won't get more than 2x, maximum 2x.
I guess fairness is not the main goal here.
But yeah. I mean, so if you're a company, if you want to invest on this hardware, you want to buy a GPU cluster, you probably want more than 2x improvement to justify the funding you will reserve for GPUs, right? For machine learning, etc., it's more than 2x, so it's fine. But these sparse solvers are so it's the judgment is money versus time versus the programming effort as well. So the story is a little different. Yes. Merhaba.
So, çözdüğünüz program neydi, örnek program? İstiyor musun?
Confidential. Yeah, so I cannot say much about it.
Yüksek hız mı mesela?
Hiç bilmiyorum detayları.
Onlar da çözümü etkilebilir.
So, I'm not sure they even gave us a real problem. I don't know.
Okay.
Yeah. It's a black box for us.
Um,
So we just had a mesh. That's all I know. It might the numbers in the
number of iterations were the same, I guess.
Number of
For the
iterations.
solver, nothing independent of the problem, right?
Yeah. So we probably get a dummy data. I don't know. So.
And IRU solver or preconditioner, is it local for each API processors or for each processors you are?
I believe SU2 partitions them because let me tell you on the CPU, we did the scaling study as well. 1 versus 24 core, you get 6-7x improvement. You don't get 24. So 6-7x, 1 core versus 24 cores. Yeah.
So for each CPU part, you do the improvement of GPU, right? So each.
No. So we are, sorry, we are comparing with one GPU with 24 cores. There's no multiple GPUs here. Yeah, there's no question. Thank you.